Once an equivalent carbon content has been determined, we can predict the approximate range of preheat that will be necessary for best results in welding. The table below summarizes some suggested preheat diagram, shows the microstructure. Base metal thickness also has an effect on the cooling rate. Generally, welds on thicker base metal cool more rapidly than welds on thin sections. The larger heat capacity, or heat sink, associated with the thicker sections produces faster cooling of the weld bead. So, when thicker sections are being welded, various welding requirements, such as preheat, may be specified to reduce the cooling rate to improve the resulting mechanical properties of the heat-affected zone. Therefore, when welding heavy sections, preheat and interpass requirements are normally increased to aid in slowing down the resulting cooling rate. There has been mention of some of the heat treatments that may be applied to metals. They can be applied to the base metal prior to welding, or to the completed weldment to produce specific mechanical properties. As welding personnel, one of your jobs may be to monitor these heat treatment operations to assure that the time and temperature requirements are being observed. The basic heat treatments include annealing, normalizing, quenching, tempering, preheating, postheating, and thermal stress relieving. Annealing is a softening treatment used to increase the metal's ductility at the expense of its strength. To accomplish annealing, the metal is raised just into the austenitic range, held for 1 hour per inch of thickness, or a minimum of 1 hour, and then cooled very slowly. In a furnace heat treatment, this cooling is usually done by turning off the furnace power and allowing the part to cool to room temperature while remaining in the furnace. Normalizing also softens the metal, but not as significantly as annealing. It is considered a homogenizing heat treatment by making the metal structure very uniform throughout its cross-section. The normalizing treatment is initiated by raising the metal's temperature into the austenitic range, holding for a short time, and then allowing it to slow cool in still air. This cooling occurs faster than a furnace cool, so the resulting properties include slightly higher hardness and strength, and possibly lower ductility as compared to annealing. Normalized carbon and low alloy steels are usually easily weldable. Quenching differs from annealing and normalizing in that the resulting mechanical properties show significantly increased hardness and strength and decreased ductility. The hardening treatment is accomplished by raising the metal's temperature into the austenite range, holding for a time, and rapidly cooling to room temperature by immersing the part in a quenching medium, such as water, oil, or brine, salt water. Quenching is performed to produce a primarily martensitic structure, which has characteristically high hardness and strength and low ductility. To improve the ductility without significant degradation of the metal's strength characteristics, a tempering treatment is usually performed. To temper, the metal is reheated to a temperature below the lower transformation temperature, held for a short time to allow the highly stressed martensitic structure to relax somewhat, and then cooled. Preheat treatments are used, as discussed previously, to slow down the cooling rate of the base metal adjacent to the weld, to allow for the formation of microstructural constituents other than martensite. Preheat is applied prior to welding. Postheat treatments are used to reduce residual stresses and to temper hard, brittle phases formed during cooling or quenching. Postheat is applied after the welding has been completed. Generally, postheat temperatures are higher than those used for preheat. The final heat treatment to be discussed is thermal stress relief, which falls under the category of postheat treatment. This was discussed earlier as a method to reduce the amount of residual stresses which are present following welding. Thermal stress relief is done at temperatures below the lower transformation temperature of 1,333 degrees Fahrenheit. By raising the temperature of the weld and base metal gradually and uniformly, the thermal stresses created by the localized heat of welding are allowed to relax. Stress relief occurs because the strength of a metal is reduced as its temperature is increased, allowing the residual stress to relax and the metal to recover. The component is cooled at a moderate rate after stress relief. This treatment will aid in the elimination of problems associated with distortion. There are two other aspects of welding metallurgy to be discussed, since they will also aid the employee's understanding of the physical principles involved in the various metallurgical changes discussed earlier. These are diffusion and solid solubility. We have previously noted that atoms in the liquid state can move about easily with respect to each other. However, under certain conditions, even atoms in the solid state can change positions. In fact, any atom may wander away, step by step, from its home position. These changes of atom position in the solid state are called diffusion. An example of diffusion is shown if smooth, flat bars of lead and gold are clamped tightly together. If they are left clamped together at room temperature for several days, the two sheets of metal remain attached when the clamps are removed. This attachment is due to the atoms of lead and gold, each migrating or diffusing into the other metal, forming a very weak metallurgical bond. This bond is quite weak, and the two metals can be broken apart by a sharp blow at their joint line. If the two metals' temperatures are increased, the amount of diffusion increases, and at a temperature above the melting point of both, complete mixing occurs. Another example of diffusion occurs when hydrogen, a gas, is allowed in the vicinity of molten metal, such as a weld. The most common source of hydrogen is moisture, or H2O, or organic material contamination on the surfaces of the parts to be welded. Many of the contaminants normally found on metals are organic compounds, like oil, grease, etc., and they contain hydrogen in their chemical makeup. The heat of welding will break down the water or organic contaminants into individual atoms, which includes the hydrogen atom, H+. The hydrogen atoms are quite small, and they can easily diffuse into the base metal structure. As they enter the base metal, the hydrogen atoms often recombine into the hydrogen molecule, or H2, a combination of two atoms of hydrogen, which is much larger than a single atom of hydrogen. The larger molecules often become trapped in the metal at discontinuities, such as grain boundaries or inclusions. These hydrogen molecules, because of their larger size, can cause high stresses in the internal structure of the metal, and for metals of low ductility, can cause cracking. Hydrogen cracking is often referred to as underbead or delayed cracking. The primary cure for hydrogen cracking problems is to eliminate the source of hydrogen. The first step is to thoroughly clean all surfaces to be welded. Another approach is to specify the low hydrogen electrodes for use on carbon and low alloy steels. These low hydrogen electrodes are specially formulated to keep their hydrogen content quite low, but they do require special handling to avoid moisture pickup after opening the sealed shipping containers. Preheating the base metals is also effective in eliminating hydrogen pickup, because hydrogen will diffuse out of most metals at temperatures of 200 to 450 degrees Fahrenheit. The methods noted can all aid in reducing the possibility of hydrogen cracking in those metals which are susceptible. Most of us are familiar with the normal solubility of solids into liquids. Adding a spoonful of salt to a glass of water and stirring will dissolve the salt. However, most of us are not familiar with one solid dissolving into another solid. In the example given above with the lead and gold, the two metals were diffusing through solid solution into each other. And returning to our example of salt and water, if additional salt is added, we find that some of it will not dissolve, regardless of how much we stir. What has happened is that for that volume of liquid and its temperature, we reach a critical solubility limit. No amount of stirring will dissolve any more salt. In order to dissolve more salt, the liquid volume would either have to be increased or its temperature raised. Thus, we see that for a solid dissolving into a liquid, there is a critical solubility limit depending on liquid volume and temperature. Metals behave similarly, except through diffusion, and they dissolve into each other when both are solid. But just like the salt and water, there are solubility limits of one solid dissolving into another, and the critical solubility limit is dependent on temperature. The higher the temperature of a metal, the more dissolving of a second element will occur. Thus, we can get metals combining even when both are solid. Of course, as the metal temperatures are raised, the amount of diffusion and solubility increase. An example of a solid dissolving into another solid is a method we use for increasing the surface hardness of a steel. If the steel is packed into a bed of carbon particles and then heated to a temperature of about 16 to 1700 degrees Fahrenheit, which is well below the melting point of both the carbon and the steel, some of the carbon will diffuse or dissolve into the surfaces of the steel. This added carbon in the steel's surface makes the surface much harder and is useful for resisting wear and abrasion. This technique is commonly called pack carburizing. The surface of steels can also be made hard by exposing the steel to an ammonia environment at similar temperatures to carburizing. The ammonia, NH3, breaks down into its individual components of nitrogen and hydrogen, and the nitrogen atoms enter the surface. This technique is called nitriding. Both of these surface hardening techniques demonstrate the diffusion and solid solubility of metals. Knowledge of diffusion and solid solubility will aid welding personnel in understanding the importance of cleanliness in welding and the need for proper shielding during all welding operations. To this point, the primary alloy used for discussion has been carbon steel and low alloy steel. This final section will review the welding metallurgy of three commonly used materials: stainless steel, aluminum, and copper, and the various alloys of each. Stainless is a bit of a misnomer when applied to the classes of metals referred to as stainless steels, since it usually means they resist corrosion. However, in severe corrosive environments, many of the stainless steels corrode at very high rates. The stainless steels are defined as having at least 12% chromium. There are many types of stainless steels. Welding personnel should recognize this when discussing them and use the proper designation for each type. The five main classes of stainless steels are ferritic, martensitic, austenitic, precipitation hardening, and the duplex grades. The first three categories refer to the stable room temperature phase found in each class. The fourth one, often called pH stainless steels, refers to the method of hardening them by an aging heat treatment, a precipitation hardening mechanism, as opposed to the quenching and tempering mechanism known as transformation hardening. The last one, the duplex grades, are approximately half ferrite and half austenite at room temperature, with improved resistance to chloride stress corrosion cracking. The stable room temperature phase found in stainless steels depends on the chemistry of the steel, and some stainless steels may contain a combination of the different phases. The more common stainless steels are the austenitic grades, which are identified by the 200 and 300 series grades. 304 and 316 stainless steels are austenitic grades. A 416 steel is a martensitic grade, and 430 is a ferritic grade. One of the common pH stainless steels is a 17-4 pH grade. A popular duplex grade is AL-6XN. As might be expected, the weldability of these grades varies significantly. The austenitic grades are very weldable with today's available filler metal compositions. These grades can be subject to hot short cracking, which occurs when the metal is very hot. The problem is solved by controlling the composition of the base and filler metals to promote the formation of a delta ferrite phase, which helps eliminate the hot short cracking problem. Typically, cracking will be avoided in the austenitic stainless steels by selecting filler metals with a delta ferrite percent of 410%. This percentage is often referred to as the Ferrite Number and can be measured with a magnetic gauge. The delta ferrite can be measured using the magnetic gauge, since delta ferrite is BCC and magnetic, while the primary phase, austenite, is FCC and non-magnetic. The ferritic grades are also considered weldable with the proper filler metals. The martensitic grades are the most difficult to weld and often require special preheating and post-weld heat treatment. Procedures have been developed to weld these materials and must be followed carefully to avoid cracking problems and maintain the mechanical properties of the base metals. The pH and duplex stainless steels are also weldable, but attention must be given to the changes in mechanical properties caused by welding. One of the common problems found when welding the austenitic grades is referred to as carbide precipitation, or sensitization. When heated to the welding temperatures, a portion of the base metal reaches temperatures in the 800 to 1600 degree Fahrenheit range. And within this temperature range, the chromium and carbon present in the metal combine to form chromium carbides. The most severe temperature for this formation is about 1250 degrees Fahrenheit. And this temperature is passed through twice on each welding operation cycle, once on heating to weld and again on cooling to room temperature. These chromium carbides typically are found along the grain boundaries of the structure. The result of their formation is the reduction of the chromium content within the grain itself adjacent to the grain boundary, called chromium depletion, resulting in reducing the chromium content below that required for resisting corrosion. The final result of this chromium depletion of the grain is a reduced corrosion resistance of the grain itself due to its reduced chromium content. In certain corrosion environments, the edges of the grains corrode at a high rate and is called interangular corrosion attack, or IGA. Sensitization of austenitic stainless steels during welding can be prevented by several methods. The first method involves reheat treating the complete structure by heating to 1950 to 2000 degrees Fahrenheit. This solution annealing breaks up the chromium carbides, permitting the carbon to be redissolved into the structure. However, this heat treatment can cause severe distortion of welded structures. Following heat treatment, the structure must be rapidly quenched in water to avoid reformation of the chromium carbides. A second method is the addition of stabilizers to the base and filler metals. The two most common examples for stabilization are the addition of titanium or niobium, columbium, to the 300 series alloys in amounts equal to 8 or 10 times the carbon content. These alloying stabilizers preferentially combine with the carbon and reduce the amount of carbon available for chromium carbide formation, maintaining the grain's chromium content and corrosion resistance. When titanium is added, we have the austenitic stainless alloy 321. When niobium is added, we have the 347 grade. The third method is the reduction of the carbon content in the base and filler metals. Initially, these low-carbon austenitic stainless steels were referred to as extra low carbon, or ELC for abbreviation. Today, they are referred to by the letter L, meaning the carbon content is less than 0.03%. The standard grades contain up to 0.08% carbon. By reducing the carbon content in the alloy, less carbon is available to combine with the chromium, and sensitization is reduced during welding. These low carbon grades have slightly reduced mechanical properties because of their lower carbon content, and this must be considered when selecting these alloys, especially for high temperature use. Aluminum alloys have a very tenacious oxide film on their surfaces, which forms very rapidly when the bare aluminum is exposed to air, and these oxide films give protection in corrosive environments. These same oxides on the surface interfere with the joining processes. To braze or solder these alloys, fluxes are used to break down the oxide film, so the parts can be joined. When welding, alternating current is used, which results in breaking down of the oxides by the current reversal of AC welding, and the reformation of the oxide film is avoided by shielding with helium or argon gas. The AC welding method is sometimes referred to as a surface cleansing technique. The metallurgy of aluminum and its alloys is very complex, especially regarding the great number of alloy types and heat treatments. The proper filler metals for most weldable grades and heat treat conditions can be found in AWS A5.10, specification for bare aluminum and aluminum alloy welding electrodes and rods. Pure copper and many of its alloys cannot be hardened by a quench and temper heat treatment as steel can. These alloys are usually hardened and made stronger by the amount of cold work introduced when forming them into various shapes. The act of welding softens the cold-worked material and must be considered before welding on work-hardened copper alloys. There is a series of copper alloys that are strengthened by aging, a treatment similar to the precipitation hardening used on the pH stainless steels. When welding on these alloys, a post-weld heat treatment is usually specified to restore the original mechanical properties. One of the major problems with welding of copper and its alloys is due to their relatively low melting point and very high thermal conductivity. Considerable heat must be applied to the metal to overcome its loss through conductivity, and the relatively low melting point often results in the metal melting earlier than expected and flowing out of the weld joint. Most copper alloys are weldable with proper technique and practice.